This lecture is on absolute convergence of series and power series. We're going to do parts of 11.4 and 11.5. I drew this little diagram here just for, oh boy, I have to move it over just a sec. Infinite series, let's just say sigma A sub n, can either be divergent or convergent. Now, we have the test for divergence that helps us sometimes, or all of the different tests that we learned in the three different tests we learned in the last video to test for convergence and divergence. We know that if a series is divergent, that means, change color here, that means that the limit of its sequence of partial sums does not exist, or it might be infinite, but there is no finite limit. Whereas for a convergent series, what it means to converge is that that sequence of partial sums does approach a limit that we might call S, and we call that the sum of the series. Of course, it's not a sum, it's a limit of a sequence. Now we're going to study two different kinds of convergence, but we are going to concentrate on this one. Section 5.4 is mainly conditional convergence, and we're only going to talk about it briefly, and we will be sticking to this kind of convergence in our class because of lack of time. Absolute convergence means that the series, the infinite series sigma absolute value of A sub n converges. That's a strong type of convergence called absolute convergence. Conditional convergence is when the series sigma A sub n does converge, but if you put absolute value signs on, that does not converge. So this is called conditional convergence. If a series sigma A sub n converges in absolute value, then that series sigma A sub n is said to converge absolutely. So this is an important word. Converges absolutely if the series of absolute values converges. Now, most of the series we've looked at, by the way, we have seen conditional convergence. For example, if you look at sigma 1 over n squared, a p series, well, those are all positive anyway. So putting absolute value signs doesn't change that. Any of our positive termed series, another one would be like 2 to the n over n factorial. These are positive termed series anyway, so they all converge absolutely. If sigma A sub n in absolute value converges, then so does the series. Now, this has a very nice little proof that I'm not going to do in the lecture. I forgot if it's in our textbook or not, but if you would like, it's a really neat proof. It uses everything that we've learned in the last couple of lectures. If you would like to look up the proof that if a series converges absolutely, then the series itself converges without the absolute value signs, I will give you extra credit. So you look it up and write it out and make sure you understand it. It's only 4 or 5 line proof, and hand it in to me, and I will change your lowest quiz score to a 10. So I'm not going to remember that, you guys. You have to just hand it in and remind me of what I promised. I'd like to show you one example. This series here, minus 1 to the n times 1 over n equals 1 to infinity. This is called the alternating harmonic series because it starts with minus 1 and then plus a half, minus a third, plus, and so on. So it's not the harmonic series, it's the alternating harmonic. This series converges, and in fact, amazingly, it is equal to the natural log of 2. That's what the sum of that series is. You don't have to memorize that. So the alternating harmonic series converges to the natural log of 2, but if we put absolute value signs on that, we would have the harmonic series, and we know that the harmonic series diverges. So it is very possible for this series to converge, but not absolutely. This is called conditional convergence, and we are not going to look at too many of those examples. As you just saw with the alternating harmonic series, it is possible that a series, sigma a sub n, converges, but that it does not converge absolutely. These series that converge only conditionally are not of practical use. So in the interest of covering more useful topics and getting on to sections 5, 6, and 7 in our text, I am going to pretty much skip conditional convergence. So we will be testing all positive termed series, because if they're not positive termed, we're going to test their absolute value. We're going to test for absolute convergence. For example, here, this example, I would not test that series. I would look at this one, the absolute value of sine j over j squared. Now, if this converges, we will say this series converges absolutely. Therefore, it converges in the regular sense, but it converges absolutely means it is an even stronger kind of convergence, as you'll see when we talk about power series. So let's see, let's use the comparison test. We know that the sine of j in absolute value is less than 1 and greater than 0. So they're positive. I could divide by j squared. Therefore, the absolute value of sine j divided by j squared is less than 1 over j squared. And sigma 1 over j squared converges. In other words, because that's a p-series, p equals 2. And we can say, therefore, our series, notice how I'm writing this, therefore, the series sigma sine j over j squared converges absolutely by the comparison test. So moving on to section 11.5, we'll start with power series. A power series is of this form. It's a function of x. S of x is equal to the sum from k equals 0 to infinity of a sub k times x minus x naught raised to the k power. So notice where the k is. K, you have a coefficient, and then you have powers of x minus x naught raised to the k power. X is not changing. X is it's a variable. You want to find out for what values of x will this series converge. X naught is a fixed number. these power series will converge for some values of x. At least they'll converge for x equals x naught, won't they? Because you just have 0 plus 0 plus 0 plus 0. So, or maybe you would have a sub 0, because the first term would have just be a sub 0. And then all the other terms would be 0. The set of x for which the series converges will be an interval centered at x naught. The radius of that interval is the radius of convergence that we call r. Let me give you an example that you've seen several times. We've answered several of these power series questions already. For example, for what values of x does x to the n equals 0 to infinity, which is just 1 plus x squared plus x cubed plus dot dot dot. For what values of x does this power series converge? Notice the a sub k here, or the a sub n, it's just equal to 1. There are no coefficients right here. And x naught is equal to 0, x minus 0 to the n. So make sure that you see that this does fit this general definition of a power series. And let's see, for what values of x does it converge? Well, we know that the absolute value of x has to be less than 1, and so we get x is in, that means is an element of the interval, minus 1, 1. Notice that this interval, minus 1, 1, is centered at x naught equals 0. So these power series will always converge on an interval that is centered at x naught. Now sometimes that interval may have radius 0. Maybe they only converge at x naught. But usually they converge on some interval centered at x naught. And the radius of convergence here we see is 1. The radius of convergence is the distance from x naught, right here, the distance from x naught to the endpoints. You see that's 1. And it's 1 in this direction because the interval is centered at x naught. So here's another example of a power series. Let's write this like the definition stated on the previous slide. This would be sigma, and the coefficient really is 1/2 to the k times x to the k. You don't have to do this, but I'm just showing you how it fits the definition. So you see here that our a sub k in our definition of a power series is 1/2 to the k, or 1/2 to the k. And again, our x naught, the center of the series, is 0. So we're going to get some kind of convergence around x equals 0. So let's see how to do this. You've already done problems like this. You know exactly what to do. This will converge because it is written as a geometric series for the absolute value of x over 2 less than 1. Take the reciprocals first. I noticed on your quizzes of the students who did not take reciprocals first ended up making little algebra errors easier. So let's see, this is, that's greater than 0, so we could take oh, excuse me. Sorry about that. This is fine. I'm sorry. So the absolute value of x is less than 2, which gives us x between 2 and minus 2. So our interval of convergence is centered at 0, which is x naught, and it goes out 2 units to the right and 2 units to the left. 2 and minus 2. So this is our interval of convergence. The radius of convergence is 2. Now, I want to say something here. It is something else that I am going to maybe show you once on a video, but we are not going to spend time on it. We do not know about the convergence at these 2 points. At these endpoints, -2 and 2, we don't know. We know that the series diverges if x is less than -2. It diverges if x is greater than 2. But at the endpoints, we're not sure. And in order to find out, we would have to test at those endpoints. I think this is our first example here, so I think I'm going to show you what I mean by testing at the endpoints, and I probably won't do it again. So let's see, if x is equal to -2, we have the series summation, well, -2 over 2 is -1 to the k from k equals 0 to infinity, and we already know that that diverges. And if x is equal to +2, we have summation 1 to the k, which of course diverges. The partial sums are 1, 2, 3, 4, 5. The partial sums diverge to infinity. And over here, the partial sums are 0, 1, 0, 1, 0, 1. So in either case, we have no limit. So then we really can say that the interval of convergence is the open interval -2, 2. Sometimes when you plug in those endpoints for x, you will get convergence, but it often is conditional convergence. In other words, the series converges, but not absolutely. Endpoint convergence is not important for power series, so I'm going to skip it. Now this problem, this series you see is not geometric, so I really can't use the method that I just used before. I'm going to use the ratio test. So let's use the ratio test and see if we can get the interval of convergence. So you remember in the ratio test we compare, and we're going to do absolute value of. We're looking for absolute convergence. So we're going to look at the absolute value. This terminology is not quite, because these aren't expressed as a sub k's, but we're looking at the n plus first term of the power series divided by the nth term of the power series. And this one, so I'm going to write it out, I'm going to write it this way. You are not going to need to do this every time, but we have the absolute value of, well, the n plus first term would be x to the k plus 1 over the square root of k plus 1 divided by x to the k over the square root of k. Now, I really didn't have to. Normally, I would just do this. I would skip this and go straight to here. You know we're going to invert this and multiply. And also, the square root is already positive, so we only need our absolute value around x. So I would write this as the absolute value of x, that's the only part that could be negative, to the k plus 1 over the square root of k plus 1. And then I would invert the a sub n, the nth term, and write the square root of k over the absolute value of x to the k. The absolute value signs are very important, but they only have to go on the parts, on the factors that could be negative. Okay, so this then is equal to, put the x's together, we have the absolute value of x to the k plus 1 over the absolute value of x to the k, and here we have the square root of k over the square root of k plus 1. Now again, this step is one that you could skip and go directly to, well, the absolute value of x to the k cancels, and I would write this, since they're both square roots, the square root of k over k plus 1. Well, now I'm ready to take the limit. I know that k over k plus 1 goes to 1. Now remember, x you're imagining as some fixed quantity while you're taking the limit. Notice that x has nothing to do with k. So it's just this here. This goes to 1, and the square root of 1 is 1. So the limit of this thing as k goes to infinity is the absolute value of x times 1. So for this example, I want to say just once, writing it all out, the limit as k goes to infinity of the absolute value of x times the square root of k over k plus 1 equals the absolute value of x. And in the ratio test, that limit must be less than 1. So I need to solve this inequality, and I get exactly the interval minus 1, 1. So this series converges on the interval minus 1, 1. Absolutely. The endpoints, it may converge conditionally, but I know that this series, the power series, that for this example, converges. I could say converges absolutely, but we'll just say converges on the interval minus 1, 1, and the radius of convergence is 1. Okay, we'll do one more example. You can see that this is a power series. If we wrote it out, this part you don't need to do, but just so you can see how it fits the definition, we would have 3 to the n over n times x minus 0 to the n. So our coefficient, the a sub n in the definition, is the 3 to the n over n, and x naught, again, is equal to 0. Okay, but we'll just go back here. You don't need to write it out this way, really, if you don't want. So we're going to start by the absolute value, I shouldn't have called that a sub n, of this is just how the root ratio test was stated. Here I'm considering the a sub i's, the whole thing. Okay, so we're going to have the absolute value. I'm going to take the 3 out. No, excuse me. I don't want to do it that way. I'm just going to do it the absolute value of 3x to the n plus 1 over n plus 1 times inverting and multiplying n over, and I only need the absolute value around the 3x to the n. Okay, well, we can do some canceling. 3x to the n plus 1 over 3x to the n just leaves us with the absolute value of 3x on the top, and that is times n over n plus 1. And we know that n over n plus 1 goes to 1 as n goes to infinity, so the limit of this is the absolute value of 3x. And we want that to be less than 1 for the ratio test to give us absolute convergence. So this implies then, dividing both sides by 3, that the absolute value of x is less than 1/3, and our interval of convergence is negative 1/3, 1/3, and the radius of convergence is 1/3. Now, we have known for a long time that the series sigma x to the k converges to 1 over 1 minus x, the function 1 over 1 minus x, for x between minus 1 and 1. Let's write out a few terms of that again. I'm going to do it up here. I should have put it on the slide. So we have 1 plus x squared plus x cubed plus dot dot dot. In the past, I've found that many students, when they're working with power series, they prefer to write out the series like this, and that is absolutely fine. So call the above function f of x equals 1 over 1 minus x. And it has domain minus 1, 1. We're not on the whole real line. Can you see that 1 over 1 plus x is f of minus x? Check it. F of minus x is equal to 1 over 1 minus a minus x, which is 1 over 1 plus x. So you can do the exact same function composition. You can take minus x and plug it in for x here in the function. You can plug in minus x. Well, we can do exactly the same thing in the long, infinitely long polynomial, the power series. So let's use this fact to find a power series representation for 1 over 1 plus x. So I'm going to write 1 over 1 plus x is the function evaluated at minus x, which will be, well, if you want to use summation notation, we're going to just put minus x in for x. Notice I put the parentheses around it. I'm going to leave the k off. We don't need it. Which will be the sum minus 1. Always get your x by itself. Minus 1 to the k, x to the k. And there you go. That's a series representation for 1 over 1 plus x. Now, this is also okay. F of minus x is equal to, now I'm just going to put in minus x here. So I would get, let's see, 1 minus x plus x squared minus x cubed plus x to the fourth minus dot dot dot. These are exactly the same. And if you prefer to work with the polynomial looking form of this series, it's absolutely fine. Now the radius of convergence and the interval of convergence would be, well, we put minus x into the function, so that has to be less than 1. And of course that's the same thing as absolute x less than 1, so we have exactly the same interval of convergence and radius of convergence as we did for f of x. Okay, we're going to do something similar here. Remember, the only series that we really know, the only power series that we know is, let's just call it f of x, is equal to 1 over 1 minus x, which is summation x to the n starting at 0, or if you prefer, 1 plus x squared plus x cubed plus dot 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 for the absolute value of x less than 1. So this is what we know. Now, could we use this and function composition to find a series for this function, a power series representation? Actually, yes, because g of x is equal to 1 over 1 minus a minus x squared. So it is f of minus x squared. In other words, we can find the function g by plugging in minus x squared into the function for f. Well, then we can do the same thing with the series. So I could write this, summation minus x squared to the n, and then change it to summation minus 1 to the n, x to the 2n. If you use the summation notation, you definitely need to pull the powers of x out by themselves. Okay, another way we could look at it, f of minus x squared, we could just go to the polynomial here and say it is 1, plugging in, minus x squared for x. Whoops. There. So we have 1 minus x squared plus x to the 4th minus x to the 6th plus ... And you see that's exactly the same. These two are exactly the same thing. But somehow it's easier to just, for many students, just to plug the minus x squared into the polynomial looking form of the series. Oh, and we need to establish the interval of convergence. Well, this will be true when what we plugged into f, the absolute value of minus x squared, is less than 1, because the interval of convergence for f is the absolute value of x less than 1. Well, this tells us that, that's the absolute value of x squared, which is x squared. So this means that x squared less than 1, and when x squared is less than 1, x is an element of the interval minus 1, 1 again. So we have the same interval of convergence. You do have to check it. Okay, this looks like a lot of writing, but actually it's very simple thing to remember. Let me just start by saying if you had a polynomial f of x is equal to 1 plus x squared plus x cubed, and you were asked to differentiate it, well, you would say f prime of x, and you would go term by term, right? Terms are part of the sum. So you would just look at each of the terms of the sum, and you would get 0 plus 2x plus 3x squared. You would also integrate f the same way. The integral of f, you would go term by term, and you'd integrate 1, and you'd get x plus 1/3 x cubed plus 1/4 x to the 4th. Now again, don't write that down. We all know that's true, but this statement here is really just saying the same thing for infinite polynomials, for power series. If s of x is equal to, and look, I left off the x minus x naught just to save in some, oh, but I didn't do it down here. I should have taken that out. Let's just make the center of the power series 0, because that's basically all you're going to work with in our class. If s of x is equal to the sum of a sub k x to the k and has a radius of convergence r, then you can differentiate that infinite series by just doing it term by term. And you can integrate this series by integrating term by term. Look, this was x to the k, and so it is a sub k over k plus 1 times x to the k plus 1. The series was a sub k x to the k, differentiating k a sub k x to the k minus 1. You can integrate and differentiate power series term by term. Another way to say this, you'll see it in other textbooks. Let me just show you. We could write, for example, let's do the integral one here. The integral of the sum from k equals 0 to infinity of a sub k x to the k is equal to the sum from k equals 0 to infinity of the integral of a sub k x to the k dx. So it says if you're integrating the power series, you can have another power series of the terms integrated one at a time. Well, we can use that amazing fact that was on the last slide about integrating and differentiating power series, we can use that along with function composition, as we did in the first couple examples, to find new power series representations for functions. For example, arctan x. Well, let's see, arctan x we know is the integral of 1 over 1 plus x squared dx. Oh, we just found a power series for this. It was, well, I'm going to do this two ways. If you're using the summation notation, then we had the sum, the integral of the sum from k equals 0 to infinity of minus 1 to the k. Just look back, we just found this one, x to the 2k, which the integral of that dx is equal to the sum from k equals 0 to infinity of the integral of minus 1 to the k, x to the 2k dx. So we're going to integrate term by term, and I'm going to do this the other way too. I think you'll might like the other way better. All right, so we have this. Now I'm going to integrate with respect to x. So I'm going to just raise the exponent by 1, and I will have summation. And let's see, when I integrate, I still have from k equals 0 to infinity. I'll get minus 1 to the k, and I will divide by 2k plus 1 times x to the 2k plus 1. And that is the answer to the question. This is a power series for arctan. Now let me show you another way to do this. We could start, you have to start by recognizing this. But instead of writing the summation notation for the power series, we could say, well, arctan x then is the integral of, and write the power series as 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th minus dot dot dot, close parenthesis, dx. The integral of the series will be equal to the integrating term by term. So we would get x minus a third x cubed plus a fifth x to the 5th minus a 7th x to the 7th plus a 9th x to the 9th minus so on. So that's your answer there. If you take a minute to see, I think it's really good to see that these are exactly the same thing. This notation is a little bit at first it's kind of hard to work with, but once you get used to it, it's a huge time saver, and it makes things actually easier. So try to for sure be able to read that notation, but and be able to expand it. For example, you've got to be able to expand the series for arctan or for any of the ones you're given in order to do something like I just did in yellow. And this is our last example. I mean, you might at first think of h of x minus 1 over 1 plus x squared. You might think of it this way, but don't write this down because it's not. You might think of it as minus, and then you have 1 over 1 plus x, the quantity squared. And you have a series for 1 over 1 plus x that we found a few slides back. But you can't square. You can't square it. You can't FOIL out an infinite sum, can you? So this just won't work. Function composition is not going to work for us. But look at this as minus 1 plus x to the minus 2. Doesn't that look like a derivative? It is equal to, well, let's see, let's put d dx, the derivative of and it would be 1 plus x to the minus 1. Let's check it. Minus 1 times this to the minus 2, and we don't need to use the chain rule. Okay, so this is the derivative with respect to x of 1 over 1 plus x. Oh, and we do have a series for 1 over 1 plus x. And that was, again, I'm going to write it with summation notation, the derivative with respect to x of the sum from k equals 0 to infinity, and it was minus 1 to the k, x to the k. Now we're going to differentiate term by term. So I could say, now remember, the first term here is a constant. When k is 0, it's a constant. That term is going to drop out. So when I differentiate, since the first term was a constant here, the sum will go from 1 to infinity. And now it's going to be, well, I'll put negative 1 to the k, that's a constant, times kx to the k minus 1. And that is the answer. Oh, well, I forgot to tell you something, I think. It's written on 2 slides ago. When you integrate and differentiate a power series, the radius of convergence stays exactly the same, so you don't have to retest. When you use function composition and you plug in something for x in a known power series, you do have to check, because the radius of convergence could change. But when you differentiate and integrate a series term by term, the interval will remain exactly the same, the radius of convergence. All right, so let me do it another way, and then we're done. We learned on a previous slide that 1 over 1 plus x was just plugging in minus x into the known series 1 over 1 minus x. And we got, using the other notation, 1 minus x plus x squared minus x cubed plus x to the 4th minus, and so on. So if I want to differentiate that, the derivative with respect to x of 1 over 1 plus x, I can differentiate term by term. Notice the front term drops off, and I get minus 1 plus 2x minus 3x squared plus 4x cubed minus, and so on. And that's exactly what you would have gotten, what you did get right here. Expand that out a few terms. When k is 1, we have minus 1 times x to the 0, which is minus 1. Plus, when k is equal to 2, minus 1 squared is 1 times 2x to the 1. And you see we're getting exactly the same thing. This is really tricky stuff, and you have to do much more than just understand what I do. Try to do these examples over again on your own, and remember the 3 things that we used. We can use function composition to determine a new series for a function by plugging in some function of x into a known series, or we can recognize a function as a derivative of a function with a known series, or we can recognize a function as the integral of a known series.